Hey, welcome back to this old tool grinding shop. Today I need a small hook-shaped boring bar like this. In fact, this is already one of the boring bars I need for this project. I'm going to grind a few more because this might be a repeat job, and while I have everything set up, it's easy enough to grind more than one. So what it is, it's a 4mm shanked ID grooving boring bar. The grooving width is 2mm and I think the depth is about 1.5mm. We have to look into CAD for that. It's ground from solid carbide on surface grinder, tool and cutter grinder, and my mill. And it's used, this is a sample piece that I cut earlier on the lathe and then milled off some material to make it visible. So you have a 4mm bore. This is made so it fits in a 4mm bore barely. You can go in the bore, then you can cut features like this pocket here, or you can go here and just do a ID groove, for example, for an O-ring. Then you just move the tool out and retract it like this. That's what we need. Let's see how I came up with the dimensions for this boring bar. Let's look at some CAD here. Here we are in CAD. And this is the part I'm going to machine, or I need to machine. At least part of the part I cut away the back end of it because you don't need to see that. And then I have a second version of this model down here that I split in half. So it's convenient to model the tool into the part. You just start out by creating the shape of this tool that needs to go in this groove and create it as a circle, and then you add a shank that's off center, and this determines the maximum shank diameter. You give it a little bit of clearance here so the shank, if there's a little bit of radius from the grinding wheel, doesn't rub on the wall of the part. And then you add some clearance angles like 10, 45 and a parallel clearance cut down here. So when you get a wireframe view like this, you get clearance here, here and here, and back here it doesn't matter. And then you just add a shank back on with the diameter of carbide you have. And that's what you need. And then you can even test it out with the move option here. You move the whole component and then you can just slide the tool around and see what's happening. With 1.3mm here, I get barely clearance here in the bore with the head of the tool, so I do not damage the bore. I can get that from this side too. As you can see, there is clearance all around against the bore around here. And when we move the tool in like this, we still have clearance, and now we go into the grooving operation and go back to a wireframe view, and this radius here, that's the final diameter, and we have clearance from here, and we have a cutting angle, of course. We have 0° top rake, which the final tool will not have, 45 here, and then just whittle away the material. So that's the way I came up with this tool. I also, off this tool, I made a little bit of a drawing to get me some dimensions here. For example, the first 15° clearance angle is about 0.8mm wide. My eccentricity for the smaller diameter shank is 0.68mm with a diameter of 2.4mm. This is just for me, so I know what I'm grinding. So I'm not standing clueless at the grinder, which I do anyway, but this gives me at least a rough idea what's going on. I'm using the Deckle S1 tool and cutter grinder to cut off the ends of these broken carbide end mills. I make those myself. This is a 75mm resin bound diamond cutoff wheel, and as you can see, this makes really short work of cutting carbide. This beats cutting a groove with a small Dremel cutoff wheel and breaking the carbide off by a lot. When you score the carbide and snap it off, you usually end up with fractured carbide, micro cracks in the base material, and it's just a mess. So using cutoff wheel is the better call. So we're over at the surface grinder because we need to neck down the carbide blanks to 2.5mm with some eccentricity. And I have a new tool for that. This is a very recent eBay score. This is a punch grinder, a punch former, a spin fixture. Some call it a tool room spindle. It's just a very universal piece of equipment for grinders, mills, basically any machine where you need to hold work and precisely rotate and index it. So these things are, everybody knows about these. I don't have to tell you much about them. A very famous one is, for example, the Herrick grind all. A much improved version would be something like a spin fixture from Newbold Engineering or Hermann Schmidt. This is, somebody removed the nameplate on it. This is most likely a Taiwanese or Chinese copy or reimagination of a Herrick Grindall #1. Fits the size of work I do quite well. Get it for next to nothing on eBay. And the seller told me it's in very good condition and used. But reality is it's unused, but it has some corrosion from storage. But it's really in very good shape. The bearings just feel like new, and the precision is there. So this might have been a rather good buy. And you can use these for cylindrical grinding, for grinding profiles onto the ends of punches like squares, hacks, and oblong radial shapes. You can use them for milling, light drilling operations. Just anything small and precise that needs to be indexed or spun around. You can motorize them with either a cordless drill or with a separate DC motor. I will do something on that purpose too. And most of them have a V-block in front here that can be moved up and down, so you can grind eccentric like this one. This is currently set for an eccentricity of 0.68mm. I just put it on the surface plate with a pin in it and move the V-block around with a rack and pinion drive until I get my 0.68mm of eccentricity. And then you put it on your surface grinder, spaced off the back rail with some blocks in a parallel. By the way, on the surface grinder, blocks without any holes are nice because it's easier to clean them after grinding. Because the V-block is rather large, I put a small ER11 collet chuck in here, which will hold my carbide blank. Otherwise, the wheel hub here would hit either the V-block or the clamping arrangement here. So yeah, that's the spin fixture. I was looking for over a year now for a used one because I started to build one myself. I had a design, but over the time I wasn't too happy with the design anymore. And since all the parts already were machined and hardened and also hard machined, I decided to ditch it. Sometimes you have to ditch a project if you're not happy with it anymore. If you get in a pickle and you find out that the design you decided on is not ideal, walk on. It doesn't help anybody if you finish a finish the project and you're not happy in the end. So I ditched the parts. I still have the spindle bearings, very high-end spindle bearings, but I will do something with it someday, but not for now. For now I have a commercial alternative here. So you move this under here, then you move this in and you crank this and you move and you drop the spindle down for grinding the neck on this tool we're creating. Here we are with the carbide split in half like this. And while we're here, this is easy because I already have it set up and aligned and everything. So I'm not going to grind the clearance angle on the tool and cutter grinder, the radial clearance. We're going to do this here on the surface grinder. So we go to 0 degree, and then we move it in 15 degrees. So this is the back side of the spin fixture with the graduated dial and the vernier. And we go to 0 and we want 15 degrees of clearance. Here we are. And then we drop the shot pin because this is 24 positions per full rotation gives us 15 degrees. If we need an angle that's between those 15 degrees, we have a lock here. Then we can move it to, for example, 5 degrees and just manually clamp it. This is also useful if you want to do milling and don't want to put the milling side loads onto the shot pin. Okay, in this case we just clean up until our clearance surface creates a cutting edge against the flat rig ground in the previous operation. Okay, there's our flat, cleaned up all the way to the edge. Now we go to 45 degrees and grind a secondary clearance angle until we have about 0.8 millimeters of the primary bevel left. We can guess that with a scale. That's good enough. It's just clearance. Here is the primary bevel in blue and the secondary bevel in blank carbide. Now we move it to 180 degrees, means the previous ground flat is on the underside now, perfectly parallel. And now we just grind the final height of the back side parallel to the cutting face. And this again is just for clearance purposes. Okay, there we go. This is all the surface grinder work that needs to be done. Now we go to the Deckle tool and cutter grinder. Not the D-bit grinder, the real tool and cutter grinder. There we go. Our ER11 collet wrench in here, and here we are. Roughed out, came out rather nice. And here's the final product next to it. Time to leave the surface grinder and we move over to the Deckle S1 tool and cutter grinder. We are using the regular dividing head here, and I have the boring bar blank already here in the collet, and we're just going to clamp it, but I need to align the top surface horizontal with the travel of the machine, otherwise we're grinding some bogus angles on here. So we get our dial test indicator in here. Now we just traverse the table back and forth and use the fine adjust here until we don't get a needle movement anymore. So that's pretty darn close. That's well within a few micron over this short distance. Then we spin our dial here to 0 degrees, just in case. So let's double check it. Let's move it to 0 and whoop, 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 across the whole surface, close to no movement. Perfect. We already have a diamond cup wheel in here. The dividing head is tilted back 3 degrees and rotated like this also 3 degrees. And now we can grind the front clearance angle in two directions and also create the final width of this cutting edge. This is oversized right now. This will cut like a 3 mm wide groove. We need a 2 mm wide groove. Okay, we ground this to 2.2 millimeters now, but I still left material on because in here I need also clearance to the back and to the bottom. I can't reach this with a regular cup wheel or with a wheel in this style. I would either need a straight wheel, which I don't have small enough with a sharp corner, or we do the old reversed cup wheel trick. So get this wheel off here, for the cutting tool. And then I have a cup wheel that I put on reversed onto an arbor. There we go. And we will have the grinding wheel spin this way, so it's grinding into the cutting edge, not away from it. We don't have to change our clearance angle since we spun the tool 180 degrees around, or 3 degrees. The direction of our 3 degrees is still valid for the back side of the tool, which is very convenient. That's the final width of the cutting edge we got. So here we are. This is basically our finished tool with all the clearance angles now. Okay, I have a V-block in the vise of the milling machine. The boring bar is held in it, and I'm using again the dial test indicator to align it parallel with the travel of the machine, and I'm using these parallel pliers here to manipulate them accordingly. Okay, that's already pretty darn good. Okay, that's good enough. So the tool I'm using here is a direct plated diamond tool that's normally used in a die grinder. A very cheap 1.5mm diameter, and we just drop it down, run it at 3000 RPM and create this nice chip breaker positive rake curl in the top of this tool. Okay, that's all. I'm moving constantly up and down so I do not strip the diamond off in a certain area. And also you have to be very careful with the infeed, otherwise you will strip the diamond off the metal carrier. So these tools are fairly rough and they'll leave a ragged surface. To refine it a little bit, we can use a piece of brass and some diamond lapping compound and give it a little bit of attention that way. This is 3.5mm micron diamond. Not super fine, but for this purpose more than adequate. Add some oil. This is just a light oil, just to keep things a little bit wet. The black sludge you see forming in the area where we touch the carbide, that is actually carbide dust that's abraded by the diamond in combination with the soft brass. And we don't need to lap the whole curl. The front cutting edge is enough if that's diamond lapped. That's also the reason why I used a 1.5mm diamond tool and then a 2mm brass rod for lapping. There we go. You can see the very narrow bright band in front of this half round curl. And that's where we diamond lapped it. Here you can see the curl from the side. So I'm very happy with this, and I will make 2 or 3 more of these so I have some stock. Yes, this is a tool I could buy from Goering or PH Horn or Micro 100, but to be honest, I'm a cheap guy. I hate spending money, and today is a slow Saturday. I don't want to work on an actual project, so I'm preparing tools for upcoming projects, or in fact grinding tools for upcoming projects. So of course you want to see the tool in action, but as this is an ID tool, it's hard to see what's happening. So I took a piece of stock, drilled it, and then I milled away half of the diameter, and due to the shutter speed of the camera, you kind of can see inside the part while it's spinning. I couldn't get it fully synced, but still you get the idea. You get a nice rotoscopic effect here. As you can see, the tool is cutting very well. This is just aluminium. The final part will be a free machining stainless steel. Would be neat to have a light synced to the rotation of the spindle. That's maybe a future project if I want to show something like this ever again. So I hope you enjoyed this tool grinding video. Thank you all for watching, and I'll be back.